Alright guys, this is day 2 of 312, and we're going to be trying to finish off where we started the last time here. So, we're going to take a look at problem number 19. So, Shinna here found that difference of perfect squares pattern. And we're trying to say, hey, can we keep using this? And so, we're going to try and start writing stuff a little bit differently just for today to kind of help us see exactly what is going on. So if I have, for instance, here 16x squared minus 9y squared, I could say, well, 16x squared is the same as 4x in parentheses, that whole thing squared, minus 3y in parentheses squared. Why that can be helpful for us, it tells us, well, the 4x is what goes in my first part, and that 3y is what goes in my second part, and one of them is positive and one of them is negative. So same thing we kind of talked about the last time, where it's the square root of that whole thing, but it's just kind of a more formal way to kind of help us get to the next thing we're going to be trying to look for. So we're going to go ahead and see, hey, can we do that for all of these things here? So go ahead and pause, try 1, 2, 3, and 4, and if you can do it, first rewrite it like this, and then factor it using that difference of perfect squares pattern, which we found. Okay, so on the first one here, we should get a to the second minus 2b to the second. And so we're going to have a and 2b, one's positive and one's minus. Here, we can do it, but this is not going to be perfect. So I would have like square root of 2x to the second power. And again, we only want to do this if we have perfect squares. We don't really want to have radicals in the things we factor out. So we're going to say we can, but we probably shouldn't do it for this particular one there. I take a look at number 3 here. Well, I see, well, I'm actually adding here, so I might think, well, hey, I can't do it. But hey, I can actually rewrite this as y to the 4th minus x squared, and then it is a difference of perfect squares, so I can do it. So I'm going to do that first, and then I'll have y to the second to the second. So y to the second is inside of my parenthesis, and then minus x in parentheses to the second. So that would be y squared minus x and y squared plus x as my two factors. Then lastly here on the fourth one, I have that plus sign here, and this is also plus, so I can't do it, right? I could try and set it up, and I could say, well, it's 2a in parentheses to the second plus 3b in parentheses to the second, but I can't factor it because there's not a difference there. It's not being subtracted, so I have to move on. All right. On number 20, so we're going to try and do it for this particular problem here. So I'm going to just kind of walk through the actual process as opposed to then kind of talking about this u and v substitution stuff. So I'm going to cover that, but in my own kind of different way here. So we have 9x squared y to the 4th minus z to the 6th. Okay, so you can say, well, how can I get this as something squared and this as something squared? And I could say, well, this would be 3xy squared minus z to the 3rd squared, right? And that works, right? And then I could set up my pattern and go ahead and work through it. But what I want you to try and take a look at and do is what's called a u substitution, right? We're actually going to use u and v because there's two things that I want to substitute, but this is effectively what we're kind of trying to do here. So I'm going to change this into u squared minus v squared. And say, well, that seems weird. I have u's and v's. Where are those coming from? Now, as a general rule, you've always been able to do this in algebra, but we don't really introduce you to it until now, because if you do it without knowing why, you're going to make problems a lot harder than they should be, right? So I'm introducing my own variables. I'm introducing my own u and my own v. Now you can do that, but whenever you do, you need to define what those are, right? So I am saying that my u is equivalent to 3xy squared, and my v equals z to the 3rd. And I'm going to say let in front of that. That's going to be more formal math thing to do, is I'm going to let u be this and let v be this. So I've defined what those new variables I have introduced are. So now I can replace any 3xy squared with u and any z cubed with v. Now I get u squared minus v squared. So what I could do now is follow my pattern and say, well, this would be u minus v times u plus v. And I'm factored, right? It's a little bit easier to factor in this u and v form than it is in the kind of ugly form. Now, once I'm done with that, with the factoring, I did all the quote unquote hard part when it was in u's and v's. Now I can plug those back in. And I'm going to get 3xy squared minus z to the third and 3xy squared plus z to the third as my factors. Done. Right? Now, some of you are probably thinking, well, that seems really dumb. Why would I waste all of my time? I could see it right there and go there. And if you could, awesome, do it, not a big deal. Okay, but I really do want you, for today at least, to try doing these u substitutions. There's going to be times in the future when we start to get more and more complex things where you really need these u substitutions in order to kind of solve these problems a lot easier. They're giving you relatively simple problems right now so that you can kind of get used to the idea and, hey, here's how it works, before they get into the harder ones where you really need that u substitution to make it easier. So for today, just try it whenever they are asking you or it makes a little bit of sense. Okay, so let's hop back over here and let's try it out on these. So here's another example of doing a u substitution. So I can say, well, let's make this make u 5x. It will make v 10y to the second. And then I can change this whole thing into this, which makes it a little bit easier for me to factor. So on A, B, C, and D here, what I want you to do is first say, hey, does a u substitution make sense here? Okay, there are going to be some of these where it doesn't make sense, so don't do it. But there are going to be some where it can help. So try and factor those and use a u substitution if it would help you here. So go ahead and pause and try out A, B, C, and D. Okay, so now that we are back, let's take a look at doing these. So A, we have, let's write that out, there we go. We have a squared plus 2ab plus b squared. Now I could do a u substitution, but it's really not going to do anything, right? I could say, well, let u be a and let v be b, but that's not going to do anything. So if I do my little box method here to factor these, right, I'll have a squared and b squared, and then I need to figure out, well, a squared times b squared is a squared b squared. What multiplies to b those and adds to be those? Well, it's going to be ab and ab, right? Because these two add to be that, and multiply to be a squared times b squared. So if I pull out my common factors, I have an a here, an a here, a b here, and a b here. So this, I actually end up getting a plus b times a plus b, also known as a plus b squared. Right? Then, if you look at b, we get x squared minus 6x plus 9. Right? So, again, we don't really need to do a u substitution here, but if we were to do one, I could do, well, like u is 3, and say, oh, this is 3 squared, and this is 2 times 3 times x, right? So if I did that, I would have x squared minus 2 times x times u plus u squared. Now, the only reason why I did this is that we can see, hey, this and this look an awful lot alike, right? All I have is a minus sign as opposed to a plus sign here. So I want to keep that in mind while I go ahead and do this out. So if I do my box for it, I'll have my x squared, I'll have my 9, and then I need to multiply it to be 9x squared and add to be a negative 6x. That's going to be minus 3x and minus 3x. So then if I factor out, I get x, and then this is 3, and then this is negative, so it needs to be a negative 3. 3, this is negative, so it needs to be negative 3. So I get x minus 3 times x minus 3, also known as x minus 3 squared. So hopefully you see how these are similar here. You can see a very similar thing here, right? I could have seen, hey, here's my like pattern. This is the exact same pattern. This is a special type which you might have learned in the past. If it's positive here, it's just a and b with a positive to the second power. If it's negative here, it's a and b the negative to the second power. So once I got here and saw, oh, this is that special pattern, I could have jumped straight down here. Okay, so that's only really going to be beneficial as far as that u sub goes if you know that pattern. But I just wanted to kind of reinforce and show that. Okay, take a look on the other side here. So C, we have 9x squared plus 30xy plus 25y squared. So that's nasty, right? We got some big, ugly numbers there. So let's do a u substitution. I'm going to make my u, let u equal 3x, and we'll let v equal 5y. Because now, if I plug these in, this will be equivalent to u squared plus, well, 3x would leave me with 10y, right? So that would be a u there. And then with a 10y, I could pull out a 5y, and I'd be left with a 2. So it's 2uv plus v squared. Hey, this is exactly the same thing as we just saw back over here, right? Back over here, that thing, this was one of those special factoring patterns, this will factor into this. So a plus b squared. So this will factor into u plus v squared. And now I can say, well, my u is 3x, my v is 5y squared, all factored. And that's a lot faster and a lot easier because I use that u substitution, which let me see that pattern. Okay. All right, and now let's take a look at D. So over here we have a plus 7 squared minus 10 times a plus 7 plus 25. Okay, so this is our first kind of different use of a u substitution. This is nasty because I could say, well, I have to multiply all of that out, distribute this, combine all my like terms, and try and factor it. That'll work, but what if I do this? I'm going to let u equal a plus 7. Now I have u squared minus 10u plus 25. Well, that's a lot more easy for me to look at and work with. Well, what if I also then say, well, let's let v equal 5. Well, then this becomes u squared minus 2uv plus v squared. And now I have that same pattern which I've been seeing, right? I have the same thing as I had right over here because it's negative. So it's going to be x or u and v being subtracted to the second power. So that's going to factor into u minus v squared. Well, u is a plus 7 minus v, which is 5, squared. Well, 7 minus 5 is going to be a plus 2 squared. A lot faster and a lot easier. Okay, so this isn't the only use for u substitutions, but it's just kind of one of those introductory uses where we can kind of say, hey, it helps us find it and see these patterns a lot easier, because like these last two, it's not very easy to see those special patterns just by looking at them originally. So we can use those u substitutions to kind of help us see those patterns and make them just make debuffing a whole lot easier for us in general. All right, so let's hop back over here for our closure. So benefits of the u substitutions is it lets us see those special patterns a little bit easier, and it can also take things that are a bit unruly and ugly and make them pretty, so that we can then work with it when it's pretty and then put it back in the end. The drawbacks to it, it does add a few extra steps. Like those first ones we saw, if you just kind of brute force it and work with those big numbers, you can get there a little bit faster, but it's maybe a little bit more challenging just because of the size and the kind of unruliness of those numbers you're working with. So there's the kind of drawbacks to it. So it's another tool that we want to add to your arsenal of things to approach problems with, but don't feel like you have to use it always and on every single problem. Okay, so with that, here is our problems for day 2 of 312. We're doing 30 through 36, and I will talk to you guys next time.